In section 3.4, we talk about zeros of polynomial functions. So the first thing is the rational zero theorem provides us with a tool that we can use to make a list of all possible rational zeros of a polynomial function. Not every number in the list will be a zero of the function, but every rational zero of the polynomial function will appear somewhere in the list. So the rational zero theorem states that if f of x is a polynomial and has integer coefficients, and p over q, where p over q is reduced to lowest terms, is a rational zero of f, then p is a factor of the constant term a naught, and q is a factor of the leading coefficient of a sub n. And so this is the important part here. We are going to take the factors of the constant term and divide it by the factors of the leading coefficient. So let's go ahead and use this theorem to list all possible rational zeros for the function f of x equals 2x to the fourth plus 3x cubed minus 11x squared minus 9x plus 15. So we are looking at just this constant term and the leading coefficient. So on top is the factors of the constant term. And we use plus or minus. So the factors of 15 are 1, 3, 5, and 15. And this is over the factors of the leading coefficient, which is 2. Now there's only two factors of 2. That's plus or minus 1 and plus or minus 2. And so now we want to divide. We have plus or minus 1 over plus or minus 1, which gives me plus or minus 1. We've got plus or minus 1 over plus or minus 1, plus or minus 2, which is plus or minus 1/2. We've got 3 over 1, which is going to give me 3, and then 3 over 2, which gives me 3/2. We've got 5 over 1, which is 5, and then 5 over 2, which is 5/2. And then 15 over 1, which is 15, and 15 over 2, which is 15/2. It's not saying that all of these are zeros, it's just a list of possible zeros. So for example number 2, for the equation 2x cubed minus 5x squared minus 6x plus 4 equals 0, we want to list all the possible rational roots and then use synthetic division to test some of the possible rational roots and find an actual root. So narrow it down to find which one is actually a root. And then we're going to use the quotient to find the remaining roots and solve the equation. So the first thing we want to do is find the possible rational roots. And that's by looking at the constant term and the leading coefficient. So we're looking at 4 over 2. So the possible factors of 4 are 1, 2, and 4. And again, the possible factors of 2 are 1 and 2. And so let's go ahead and divide and simplify. We've got 1 over 1, which is 1, and then 1 over 2, so 1/2. We've got 2 over 1, which is 2, and then 2 over 2 simplifies as 1. We don't need to list it twice. And then we've got 4 over 1, which is 4, and 4 over 2, which is 2, and again, it's already listed, so we don't have to list that twice. So we're dealing with 8 different possible rational roots. Now we could go through and try to figure out which one it is, but I'm just going to tell you which one. It's going to be 1/2 is the one we want to test. And so listing all the coefficients for our synthetic division, we get 2, -5, -6, and +4. We want to bring down the first term. We've got 2 times 1/2, which is 1, and -5 plus 1 is -4. -4 times 1/2 is -2. And -6 plus -2 is -8. And -8 times 1/2 is -4. And 4 plus -4 gives me 0. And so that means that 1/2 is one of our roots. So let's go ahead. We have our x minus 1/2 as an answer. And then from the division, we're left with 2x squared, because we started with 2x cubed, minus 4x minus 8. And we're going to set this equal to 0 so we can find the rest of the roots. So coming up to the right-hand side here, we can actually take a 2 out of all the terms of the second polynomial. So I'm going to bring that 2 right up front. And what I have left over is x squared minus 2x minus 4. So let's go ahead and factor, if possible. So a times c gives me 1 times -4, which is -4. That means I need to have 1 plus and 1 minus. And the factors of 4 are 1 and 4 and 2 and 2. Now none of those add up to -2. So that means I need to go to the quadratic formula. So x equals -b, or -2, plus or minus the square root of -2 squared minus 4 times 1 times -4. And then all over 2 times a, or just 2. And so simplifying, -2 is going to give me +2. And then we've got 4 plus 16 all over 2. And that simplifies to 2 plus or minus the square root of 20 all over 2. And we can simplify the square root of 20 as 2 plus or minus 2 square root of 5 all over 2. Now we have a 2 in common on the top and bottom, and so we can really simplify this to as 1 plus or minus the square root of 5. And so that means my solutions, I have the original one we found, which was x equals 1/2. And I also have x equals 1 plus or minus the square root of 5. And you'll notice that that 1 plus or minus the square root of 5 did not show up in that original list that we had. And that's because this is not a rational root. It's irrational. And so properties of polynomial equations says that if a polynomial equation is of degree n, then counting multiple roots separately, the equation has n roots. So that means from the previous example, we had a third degree polynomial and we ended up with 3 roots, 1/2, 1 plus root 5, and 1 minus root 5. If a plus b is a root of the polynomial equation with real coefficients, then the complex imaginary root a minus bi is also a root. So it comes in pairs. The fundamental theorem of algebra, if f of x is a polynomial of degree n, where n is greater than or equal to 1, then the equation f of x equals 0 has at least one complex root. The linear factorization theorem says that if f of x is a polynomial where n is greater than or equal to 1 and a sub n is not 0, then f of x is equal to a sub n times x minus c1, x minus c2, all the way down till x minus cn, where c1, c2, cn are complex numbers, possibly real and not necessarily distinct. In words, an nth degree polynomial can be expressed as the product of non-zero constant in n linear factors. So if I have a third degree, I can separate it as 3 linear factors. And so we're going to use this idea to find an nth degree polynomial function with real coefficients satisfying the given conditions. N is 3. 4 and 2i are zeros, and f of negative 1 equals negative 50. So n equals 3 is the degree. If 2i is a 0, we know that they come in pairs. So negative 2i is also a 0. And so we can set this up using the above theorem. So we have f of x equals a sub n. We'll figure that out afterwards. And we want to write down our 3 zeros. We had 4 as a 0, so x minus 4. We have 2i as a 0, so x minus 2i. And we have negative 2i as a 0, which we can write as x plus 2i. Let's go ahead and factor this so we can see what we're working with. I'm sorry, let's multiply, not factor. I'm going to multiply the x minus 2y and the x plus 2y first. That gives me x squared plus 2xi minus 2xi minus 4i squared. And so those two middle terms are going to cancel. And we have to remember something about imaginary numbers. I squared is equal to negative 1. And so we end up getting a sub n times x minus 4. And then we get x squared, and negative 4 times negative 1, this is going to turn into plus 4 because of that I squared. Let's go ahead and multiply these two sets of parentheses. This gives me x cubed plus 4x minus 4x squared minus 16. And I'm just going to rewrite this so it's in descending order. So x cubed minus 4x squared plus 4x and minus 16. Now we've used almost all of the information that was given. The only thing we haven't used is the fact that f of negative 1 equals negative 50. We're going to use this to figure out what this a sub n should be up front. So let's go ahead and plug that in. So f of negative 1, that's a sub n times negative 1 cubed minus 4 times negative 1 squared plus 4 times negative 1 minus 16, and this was equal to negative 50. And so we have a sub n times negative 1 cubed is negative 1, negative 4 times negative 1 squared, which is 1, plus 4 times negative 1, which is negative 4, and then minus 16 equals negative 50. And so negative 1 minus 4 minus another 4 minus 16 gives me negative 25. And since we're solving for a sub n here, we're going to divide both sides by negative 25. And so that means that a sub n equals 2. And so what we want to do is we're going to plug in that 2 that we just found back into this equation. So f of x equals 2 times x cubed minus 4x squared plus 4x minus 16. And we're just going to distribute to get our final answer. So that's 2x cubed minus 8x squared plus 8x minus 32. And that's the function that we were looking for. And so if you were to now go backwards, you would find that 4 and 2i and negative 2i are zeros. And the last thing we're going to talk about is Descartes' rule of signs. So this provides even more specific information about the number of real zeros that a polynomial can have. The rule is based on considering variations in sign between consecutive coefficients. So let f of x be a polynomial with real coefficients. The number of positive real zeros of f is either the same as the number of sign changes of f of x, or less than the number of sign changes by a positive even integer. The number of negative real zeros of f is either the same as the number of sign changes of f of negative x, or less than the number of sign changes of f of negative x by a positive even integer. If f of negative x has only one variation in sign, then f has exactly one negative real zero, and the same goes for if f of x has only one variation in sign, then f has exactly one positive real zero. So the test is the same for positive and negative. The only difference is with positive, we're looking at the original polynomial function, and with the negatives, we're plugging in a negative x and looking at that function. So let's go ahead and try this for example number 4. So use Descartes' rule of signs to determine the possible number of positive and negative real zeros for f of x equals x cubed plus 4x squared plus x plus 4. So for positive real zeros, we look at the original. and we look at the sign changes. So from x cubed to 4x squared, that's positive to positive. From 4x squared to x, that's also positive to positive. And x to 4, those are both positives. Every single sign on the terms here is positive, so there are no sign changes. Which means there are 0 positive real zeros. That means that they would only be negative. Now let's look for negative real zeros. We need to plug in negative x to do this. So that's negative x cubed plus 4 times negative x squared plus negative x plus 4. And simplify it. So negative x cubed ends up giving me negative x cubed. 4 times negative x squared is still going to give me 4x squared. We have negative x and then plus 4. So let's look at the sign changes here. We go from negative x cubed to positive 4x squared. So that's one sign change. We go from positive 4x squared to negative x. That's positive to negative, so a second sign change. We go from negative x to positive 4. Again, another sign change. So that means, by the rule, it says we have 3, since that's how many we found, or it's less than the number of sign changes by a positive even integer. Well, positive even integer is 2. So that means we have 3 or 1, because we need to subtract 2 off, negative real zeros. So we have 0 positive real zeros, and we have either 3 or 1 negative real zeros.